All right, we'll go ahead and get started while some other folks join us for the webinar. So welcome to our Pigments 101 webinar for May. We're happy that you're here, especially after a long holiday weekend. We are going to dive a little deeper this month into the CPC Blues as an extension of what we did last year. So we are recording this webinar. So for those of you who are in attendance today, you'll get the link to the recording as well as the PDF of the presentation. And if you have any questions along the way, just feel free to use the chat box and I will address them at the end of the presentation. Or if you want to contact me directly, feel free. My contact information is included in the presentation materials. So with that, we'll go ahead and get started. So one of the things that I found very interesting, I have to give a little shout out to Bob Ross because of his snowy accents, but phthalo blue is a pigment that you've seen thousands of times, but may not have put the phthalo name to it, to the color, because it's everywhere, in the sea, the sky, and in case of Bob Ross, in his snowy accents in all of his paintings. So the phthalo blues are part of the organic pigment category. They are a metal complex, and they are a little bit of history here. Scottish dyes used to produce phthalimide, which is a fine white solid by reacting phthalic anhydride and urea. The reaction was carried out in a glass lined mild steel vessel, which yielded a bluish green colored product. This was considered an impurity, and it was called iron phthalocyanine. The name phthalocyanine originates from the Greek term naphtha for mineral oil and cyan for dark blue. And the term phthalocyanine was first used by R.P. Lindstedt in 1933. So in the first part of this of the CPC discussion, we talked about polymorphism or crystal modifications. And I mentioned that there are a large number of organic pigments from different classes that do have polymorphic properties, in which they are apparent in more than one modification or crystal structure. So polymorphic, modification, crystal structure, they're all synonyms for this particular feature of this chemistry. Copper phthalocyanine blue is one example of a polymorphic pigment because it does occur in many different forms. However, the alpha and the beta forms have the most common commercial importance. For those of you geeky types like me, the alpha blue is on the left-hand side of these XRD graphs, and the beta blue is on the right. So you can definitely see that these are different crystals by the intensity of the absorption at the different diffraction angles. The polymorphism is responsible from the copper-copper spacing. So the center atom in the middle of this matrix is the copper atom, and depending on how close they are to each other, defines what modification it is. So in terms of the alpha, they are they are closer together. Which the alphas include the 15-0, the blue 15-1, and 15-2s. With respect to the betas, they have a less overlap or larger spacing, and these include the pigment blue 15-3 and the pigment blue 15-4. So all of the phthalocyanines start with crude blue, and from there, the modifications that are done in the synthesis part depicts whether you are going to achieve a 15-3 and or the alphas, the betas, or the greens, and also the additives are made from the crude blue as well. And these additives can be done in can be used within the manufacturing of the alphas and the betas, or they can be used as an ingredient in different applications as well. So a brief process of the alpha blues. The key area is in the first steps, where the crude blue is dissolved in sulfuric acid, and acid pasting. This acid pasting is then precipitated out to create those alpha blue particles. And once those alpha blue particles are created, they are cleaned up, filtered and cleaned up, and then the actual pigmentation is created by growing those crystals to the appropriate size and surface treating them per the end application. And then the last steps, as we've talked about in the past, are the finishing steps, which then dries and pulverizes the pigment to meet the end application. For those who like a little bit of a diagram to go with the words, so the crude blue and the sulfuric acid come together in the reactor in that first step. And then the key part is the precipitation of that slurry in the drowning tank, which creates the initial crystal for the alpha blue process. And then from there, as I mentioned, it is cleaned up, and the crystals are then grown to the appropriate pigment size that's required. Additional treatments are added if needed, and then it is filtered, dried, and pulverized. So as I mentioned, everything starts with the crude blue, which is the picture on the left-hand side, the number 1. And then for the alpha blues, the precipitation step, as I mentioned, is the key for determining the alpha blues. And that middle picture is the TEM of those initial crystals that are created when the crude blue is dissolved in sulfuric acid. The final picture on the right-hand side, a number 3 picture, is when those crystals in the middle are then grown into the appropriate size, and that pigment is then created. If we compare that to the beta blue process, here the same crude blue is then ball milled to reduce the size of that crude as the initial step. That's what makes a beta blue. This milled crude is then processed to grow the crystals directly from that aspect of it by putting them in solvent with additional surfactants to grow those crystals into the pigment. And then once the desired particle size is achieved, the solvent is removed and the slurry is cleaned up, and additional additives or surfactants are added to create the final pigment that is determined based on the application. And for the process for here, as I mentioned, the crude is ball milled to reduce the size. That's the key step for the beta blues. And then that reduced size crude is brought into the pigmentation kettle, where it's first mixed with solvent and additives to start to grow the crystals. Then the solvent is removed, and water and other surfactants and additives are added, and that is then transferred over to the treatment tank, where that final pigment is then cleaned up and filtered and dried and pulverized. So the pictures that go along with here, again, the same crude blue is the initial raw material going in, but the ball milling step that I mentioned that's key for the betas is in that second picture. So you can see that the size of these particles are considerably smaller than the starting crude. And then in the final pigmentation step, the crystals are brought together and grown to create that final pigment. So I've used this chart before, so nothing new here, but I did want to keep in the forefront that about 75 to 80% of the pigment performance does come from that chemistry. And the remaining 25% or so is the surface treatment and the finishing steps that really just tailor the performance to the specific need. However, the key thing here as a supplier, manufacturer and supplier of pigments is we want to make sure that we match the appropriate product performance with your need. So regardless of whether the pigment was designed for a plastic or an ink, we want to make sure that you get the appropriate performance from the product so that we match all of those up together. So I mentioned in an earlier slide that one of the things that you get from the crude blue is what we call a phthalo additive. And so I did mention that these are also used internally in the preparation of the pigment, as well as it's being used for other things like synergists are defined from phthalo additives. But for pigmentation, the phthalo additives help us to regulate that crystal growth during the synthesis. As you can imagine, that growth process is very critical in determining the outcome of that particular product. In applications, it also helps rheologies for inks and coatings. It helps to exhibit non-crystallizing and non-flocculating properties. These are especially noted for the 15-2s and the 15-4s. And then for plastics, it helps with heat stability. And overall, the phthalo additives improve dispersibility in all applications. So colorants provide the visual stimulation that we need. It attracts your customers, it delivers your message, and it enhances your brand image. But for phthalo blues, your color is limited. Do you want to use the red shade or the green shade? Those are your choices that are out there. In terms of the application, you still have to consider what kind of substrate you're using, what type of resin system is it's going into, and then any potential interactions within the formulation. I've crossed out indoor, outdoor, light, and weather fastness primarily because all of the CPC Blues are equal and very good in this area, but it is something to consider. Performance, of course, is always going to be application dependent, so there's a long list of things to consider in each application. Compliance, again, is also going to be application dependent, but it is key to understand where each of these products fall in terms of the various compliances that are out there. And then, of course, cost and value. Certainly, the dollar per pound is something to consider. However, the value in use is also something to consider. So, for example, there might be a product that might have a higher dollar per pound price tag associated with it, but it might also provide you an exceptional property that you need for your application. So the additional cost might be of value to you to get that additional property. In terms of compliance, I did want to point out that for the most part, all the CPC Blues, the 15-1s, 2s, 3s, and 4s are all equal and are all pretty much registered and appropriate for all regulations and inventories. The one exception is in the Pigment Blue 15-4, which does not carry the FDA regulations with it. So I've mentioned it's always going to be a balance in your colorant selection process to make sure that the pigment performance is matched with your application performance needs. And that's where we are here to help. We want to make sure that we match the appropriate product for what you are looking for, regardless of whether it's a coatings grade, plastic grade, or an inks grade. It's the actual application that we want to match to give you all that you need out of that particular pigment. So going into some data to give you a feel for what options are available. So what I've done here is I've taken all of the Sudarshan CPC Blues that are available on a global basis or around in all the regions. I've put them in a solvent-based polyurethane coating and taking a look at the color differences between the two. And in this case, because it is a transparent, I chose to use a deep tint tone color formulation, which is a 50-50 TiO2 blend. And so you can see in this type of formulation that the yellowness and blueness are pretty narrow in terms of that, which is what you would expect from blue colors. It's the red-green differences that you see. And I've added here the alpha-beta line between the two types of crystal structures. So on the right-hand side are the alphas, the red shades, and then the left-hand side, of course, are the betas, the green shades. So there's a wide variety of color that you can get. This graph here shows a difference of about 7 units from the reddest to the greenest. And then if you take those same grouping of pigments and put them in a 1090 or the typical tint tone color, whereas 10 to 90 TiO2, the distinction between the alpha and the beta becomes larger, and then the groupings, the differences between each category of pigments becomes a little bit tighter. Little less tight with respect to the betas, where the 15-3s are grouped over to the right-hand side of that grouping, and the 15-4s are going to be even more green than the 15-3s. So now if we take a little deeper dive, here I am taking a look at one pigment in each crystal category and comparing it in different types of applications. So here we are taking a look at a powder coatings formulation in that same deep tint tone color, the 50-50 mixture with TiO2. And in this powder coating formulation, you can see that there's not a lot of distinction between the alpha and beta line, where the pigment blue 15-2 and the pigment blue 15-3 are right on the same line in terms of the red greenness. However, the 15-3 is a much more blue in terms of this application, so it does develop its color more so than the 15-2 in this powder coating formulation. If we take these same 4 products and put them in that solvent-based polyurethane liquid coatings formulation, here we see a bigger distinction between the alpha and the beta line between those 2 products. And so there's definitely a distinction between the 2. If we bring these 2 to the same chart with the same axis legends here, we start to see where the difference in formulation makes with respect to each of these products. So the ones I've highlighted here are the alpha products. The very small markers are the liquid coatings, where the big markers are the powder coating formulations. So for the alphas, the liquid coating formulations develops more blueness, which is to be expected, a more intense dispersion process than the powder coating formulation. And the same is true with respect to the betas as well. In both cases, the liquid formulation develops more green and more blueness with respect to the color development. So as I mentioned, formulation and dispersion process is what will result in your ultimate color. So in comparing these two coatings processes, the powder coating formulation and process develops less red and less blue overall than the liquid. So in terms of performance properties, here we are taking a look at 15-3s that were developed for plastics, coatings, and inks applications. And in this particular one, we're taking a look at impact resistance in a powder coating formulation. So on the direct, the plastics and the coatings perform equally, while the inks grade falls off on the direct. But if you take a look at the reverse properties, the plastics still outperforms the coatings grade, and then the inks grade still is inferior to the other two. Taking a look at the Pigment Blue 15-3s in the plastics matrix, here we're taking a look at the color development, in this case, the full tone color. And the line that I have here, it shows how a 15-3 should develop color. So it should develop, go more blue and more green based on the extent of dispersion. And then in each case, we have a couple of coatings grades, a couple of inks grades, and one plastics grade of 15-3 that we are comparing. So in this case, we see a plastics and a coatings grade develops the most blueness, which makes sense because it shows that it is dispersing the best of all these pigments. However, the inks grade that I have here is more green. However, it doesn't disperse as well, showing that it is less blue. So again, it's a choice of where you need to be for your color development needs, as well as performance. If we take a look at the tint tone in the same plastic formulation, the groupings become a little bit more distinct, where the one ink grade does stand out even more than the other two. The scale on this chart is much more narrow. So the red greenness development between these grades is a lot less in the one grouping at the bottom there. However, there is a distinct difference between the development of the blueness, where the coatings grade and the plastics grade are the most blue in terms of its color development. From a performance perspective, here we're taking a look at these same 15-3s, and we're taking a look at the filter pressure value, or a measure of how dispersible these pigments are in this particular plastic matrix. And in this case, we see both the plastic grade, the coating, and the two coatings grades are equally successful in this particular property, with a filter pressure that is below 2 bars per gram of pigment. The two ink grades are not acceptable in this particular property, with the one ink grade being exceptionally poor in this particular property. So if we shift gears a little bit and compare the same type of modification, crystal modification in different chemistries, here we're taking a look at two different chemistry types of powder coating formulation and comparing the property of pellet flow between these two formulations. And in this particular case, I have two coatings grades and one ink grade in the comparison. The number one formulation is a polyester-based powder coating, and the number two is an acrylic epoxy hybrid formulation. So if we just compared the polyester formulation, all three grades of pigments perform equal. so there's no difference between the two. However, if you shift over to the acrylic epoxy hybrid, here we begin to see differences within the grades as well as across grades. So in the two coatings grades have a different response in this particular property in the epoxy acrylic hybrid formulation, and the ink grade also performs better than the one coatings grade. So again, it's always key to make sure that we match the property with the appropriate pigment, regardless of what it was developed for. So continuing on the theme at comparing the crystal structure differences in terms of properties, here is the same powder coating formulation, taking a look at gloss. And in this particular property, the 15-3 modification provides the highest gloss of all 4 modifications in this formulation. And in overbake stability, again, same powder coating formulation, it is the 15-1 that has the best performance of all 4 modifications for this particular property. So the other thing to consider when we take a look at pigments and applications is how the one pigment might look in different applications. So we've taken a look at a number of different grades in certain applications, and now we're shifting gears and taking a look at a single pigment in different applications and how it develops. So in this case, we're taking a look at a Pigment Blue 15-1. It is a plastics grade pigment, and we're taking a look at its color development in a liquid, a powder, and powder coating formulations, as well as a plastics formulation. And so the first thing that I wanted to point out was the liquid, which is the blue dot, and the plastic, which is the gray dot. They develop very similar color. However, the strength or the L value is far less in the plastic formulation than in the liquid formulation, which makes a lot of sense because the dispersion intensity of a plastics dispersion process is a lot less than a liquid dispersion process. The interesting thing to note is that the same pigment, when put into this particular plastics or this powder coating formulation, develops a lot more chroma and hue than the same pigment in other applications. We can see that this has a higher strength indicated by the lower L value, but it also is more red and more blue, which tells me that this particular pigment is well matched to that powder coating formulation and process. Now, if you have the challenge of having to match a liquid formulation to a powder formulation, could be a challenge. However, it's always good to see how the color moves in here. So in this particular case, if I wanted to match the powder formulation to the liquid formulation, I just need to lower the amount of pigment in this particular blend to a 298 TiO2 to get the similar L value and color value. So there's more value in use of this particular pigment in the powder coating formulation, and that allows us to match the formulation that develops from the liquid formulation. So the 15-1 is part of the alpha group. These are, as I mentioned, red shade in color. These pigments are used when you want to develop a warmer blue in terms of color. And if you use this color to create a green, the green that you'll get is a more natural in terms of its color position. And I have an example to show you at the end as well. The 15-1s are transparent, they're highly staining and reliably light fast. And primarily 15-1s are used in coatings and plastics. And you can see we have a number of products to offer in both of these applications, as well as cross applications. The other alpha is the 15.2. Primarily, these are used in coatings formulations, and the key here is that these particular modifications have improved surface properties for water and solvent-based formulations to improve some of the rheology that comes along with it. And then these are similarly same types of properties here. Shifting over to the betas, these are green shades in color, and these are used for when you want to establish a more cool blue color. And unlike the alphas, the greens that you get are more synthetic or maybe fluorescent type of a color aspect of it. The betas then are used in all applications in coatings, inks, and plastics. Sudarshan recently launched last year our Sudajet brand for inkjet applications. So you've seen some of those products in the data that I showed earlier in here. So you can see, because they are used in multiple applications, our portfolio of Pigment Blue 15.3s is quite varied to be able to meet all of the application needs that are out there. And then lastly, the Pigment Blue 15.4s. These are primarily used in coatings and inks. These are highly known for good flocculation resistance. One of the things that we have noticed lately is that our Sudafast Blue 2796 also happens to be a very good option for low warping for plastics. So as I mentioned, this was developed for a coatings application. However, it does have a good use for plastics as well. So I mentioned the difference between a warm green and a synthetic, or a natural green and a synthetic green. So this is just a little bit of an example that I wanted to share with you about how to get there. On the left-hand side is the alpha blue, and then when you mix it with a lemon yellow shade, and you can go down the line there and start to see that the green that you are developing is a more natural looking green when compared to the right-hand side, which is the beta blue. When you combine it with that same lemon yellow in the same proportions, you start to get a little bit more of a as I use the term, synthetic green look to your color. So depending on where you want to be, you might want to choose your starting blue form carefully. So our phthalates are a part of our Sudafast brand of pigments. They're also included in our Sudajet for the inkjet applications. So next up, we will take a look at dispersants and pigments. You can't have pigments without dispersants, and dispersants wouldn't really be needed if you didn't have pigments. So I think this will be an interesting topic to take a look at how the two are interrelated and need each other. That'll be held on June 28th. So take a look for that invitation to come out the week of June 20th. And then in July, we will take a step back and take a look at how a colorant is developed and what that process is to go from an idea to an actual launched product to offer our customers. So take a look for that in July. So I am only one part of the North American team here, but you can reach out to any one of us if you have any questions or needs. We are all here to help you and support with your application needs. So feel free to reach out to any one of us. So at this point, I'd like to open it up to any questions that you might have. And I'll go over to the chat box to see if there's anything there to be able to have. Okay, I don't see any questions here on the chat box. However, if you have any questions after you've left the webinar and or you've reviewed the materials, feel free to reach out to us. We're here to help. And so with that, I will end the webinar for this month, and we do look forward to seeing you next month to continue our series. Hope you have a great rest of your day, and we look forward to talking to you more. Take care, everybody.